Hello guys, we were talking about minors and cofactors in the last class. So we are continuing with the same topic and we'll see certain properties on that which I also had mentioned. So today we're going to see with an example and then we look into the properties of the determinants. And today's class will be like very important for you to understand the properties of determinants so that we'll be able to continue with the problems. Minors and cofactors. Minor of an element Aij of a determinant is the determinant obtained by deleting ith row and jth column in which that element Aij lies, and this minor is given by Mij. It is given by Mij. We have used this already. Definition 2, that is cofactor of an element. Cofactor of an element is given by what? It is given by capital Aij, and its formula goes like this: Aij is equal to minus 1 raised to the power of I plus j into Mij, and this minus 1 to the power of I plus j will give you the sign convention of a determinant. So if you are getting a element which is present in second row and third column, for example 2 plus 3 is 5, then you will get minus sign in that place, and that is how the sign convention of a determinant will have. Every place has its own sign, will have its sign plus, minus, plus, minus, plus, minus, plus, minus, plus, and the diamond shaped places will have negative sign. Please take this, because when we are doing the problems we are going to take this sign to take out all the cofactors. So what is cofactor? Cofactor is given by capital Aij, and the formula for that is minus 1 raised to the power of I plus j into its minor Mij. And how is minor taken out? Minor is taken out by deleting the respective ith row and the jth row wherever Aij is, and the remaining elements we take out the determinant value. That determinant value will be the minor, and when you attach this minor, when you multiply this minor with the corresponding plus or minus of that place, then you get the cofactor of the same element. Okay, so now that we have seen about minor and cofactor, we are going to the example where the concept will be very clear. Here we have an example. Yeah, we have determinant delta is equal to 2 minus 3, 5, 6, 0, 4, 1, 5, minus 7. So in this particular example, I shall show you how to take out the cofactors. After taking out the cofactors, all the cofactors are put into a matrix, and that I call as cofactor matrix. Now using this matrix and the cofactor matrix, we shall prove, we shall see the meaning of these two properties. You have two properties here, where if elements of the matrix are multiplied by their own cofactors, we get the value of the determinant. And then the second property is, if you multiply the elements of any row or column with the cofactors of another row of any other row, will be exactly equal to 0, and then added, of course, multiplied and then added, will always give you determinant value if it is their own cofactors, or if it is different cofactors, then sum will be 0. So now that will be fantastically understood when we take up this example, numerical example. So let us go for this delta. Before that, I will say I have the matrix A. I shall take, they have given the determinant, I shall take the matrix A as 2 minus 3, 5, 6, 0, 4, 1, 5, minus 7. I have the matrix. Now I shall take out the cofactors of these elements. Now to take out these cofactors, I have told you the method yesterday. I shall show you the cofactor individually how to take out for one element. Then I shall give you one shortcut method how to take out the cofactors. Okay. So this is an important class. Please be alert. Just run along with me. Now I want cofactor of say 4. I want cofactor of this 4. How do I do? 4 is present in, this is an element which is in the place second row and the third column. So this is called as A23. So I want the cofactor of A23. For this I will take the sign first. See, minus 1 raised to the power of 2 plus 3 will give you 5. And this place, actually that place will have minus, we should know as such, no need of adding up. So I shall say minus 1 raised to the power of 5 into the minor of this. How do you take out the minor? Wherever 4 is present, that column and that row you delete, the remaining elements you take out the determinant. That will be determinant of 2 minus 3, 1, 5. which will be equal to minus 5 2s are 10 minus 3 will become plus 3, and this is equal to minus 13. Okay, so now this is the way of taking out cofactor. Now to take out the cofactors of all these 9 elements, there is a method which I can tell you in a very simple way. Please get along with me. Be alert, because we need this for the matrix method, which is a 5-marker question for the exam. See, I shall tell the cofactor matrix as CA, and I shall show you how to take out the cofactors. I have 9 elements in the matrix and I want 9 cofactors, is it not? The corresponding 9 cofactors I need. I am making 9 boxes. See, all the middle boxes will have minus sign according to sign convention. So, I shall take minus there. And how do you fill up the cofactor? To take out the cofactor, I need determinant of one particular 4 numbers, is it not? So I want cofactor of 2. Wherever 2 is present, that column and that row I will delete, and the remaining 4 I will I'll fill up here. That will be 0, 4, 5, minus 7. Next, this box, that is cofactor of minus 3. To obtain this, wherever minus 3 is present, that you take out. The remaining 4 elements I'll put here. That will be 6, 4, 1, minus 7. Next is for 5, I will delete this row and this column. So you get 6, 0, 1, 5. Now to obtain this, children, there is another one simple method. See, this has been to obtain these boxes numbers. We have used R2 and R3, second row and third row in the given matrix. So in a simple way you learn like this. Use R2 and R3, close the first 2 elements, the remaining 4 are here. Next 2 you take out, then the remaining 4 are here. The next 2 you take out, the remaining are here. Okay. So now like that, go to row number 1 and do the same procedure. Close the first element, you will get minus 3, 5 and I fill it up here. Then the close this, you will get 2, 5. Then close this, you have 2, minus 3. Okay. And now the first row and the last row will be same. Copy it. 0, 4, 6, 4, 6, 0. And then the even rows R2 and R4 will be ditto. Copy them. So R2 and R4 I'll write as it is. 5 minus 7, 1 minus 7, 1, 5. Odd rows will be same. Okay. So R3 and R5 will be same. I'll copy it. Minus 3, 5, 2, 5, 2, minus 3. Now you would have taken out the determinant required for the cofactor for every corresponding element. So let me see now. I want cofactor of 5. 5, wherever it is present, that column and that row you leave, which means I need this. See, in this place you have 2, 5, 6, 4. You have got 2, 5, 6, 4. So this is one of the easiest method to take out cofactor. Once you learn this method, few seconds you can get the cofactor matrix. Otherwise it takes a long time. Not only that, it occupies more space also in your worksheet. You can see in your textbook they would have taken out A11, A12, A13, it's like that. So let us learn this method. Now I shall repeat this filling up. Please go through. I shall repeat how to take out the CA matrix. So I shall say CA is equal to, I shall make 9 blocks. Then use R2 and R3 to fill up these 3 boxes. Close the first element 6 and 1. The remaining you write here in the same orders 0, 4, 5, minus 7. Next you close this, the remaining elements you write, that will be 6, 4, 1, minus 7. Then you close these, the remaining you write, that will be 6, 0, 1, 5. And use the same method to fill up the row number 3 here using row number 1 here. So in row number 1 I'll close 2, you have minus 3, 5. I'll close this, you have 2, 5. I shall close this, this will be 2, minus 3. And then you please understand, the first row and the last row will be ditto. I'll copy. So 0, 4, 6, 4, 6, 0. Even rows will be ditto. R2 and R4 will be ditto. So I'll copy. 5 minus 7, 1 minus 7, 1, 5. R3 and R5. So let me write this, and this will be the same. R2 and R4 will be same. R3 and R5 will be same. So R5 I am filling up, copying from R3, minus 3, 5, 2, 5, 2 minus 3. Now this will fetch you the cofactors when you take out the respective determinants. So I shall take out, and now please give the presentation the way I am giving only. We are going to follow the same thing for a 5-marker problem. And now here, when I am taking out the cofactors, I shall first take out for all these middle boxes, because they are supposed to be multiplied by minus. Okay. So because that follows the formula minus 1 raised to the power of I plus j. So for those cofactors, I should be multiplying by minus. So I shall take out the middle boxes first. You have, so for all this, if you have to do any simplification, you can do on the top of this. You have minus 42 minus 4. So it is minus 46, minus into minus, plus 46. Then I'll come here, 5 2s are 10, 10 plus 3 13, 13 into minus will be minus 13. Then this box, 4 2s are 8, 8 minus 30, 8 minus 30 is 22, and minus 22 multiplying by minus. Then this, 7 3s are 21, minus 25, 21 minus 25 is minus 4, into minus will give you plus 4. Now the remaining blocks I'll finish. There is nothing to, you don't have anything extra to multiply, so it is just direct determinant. 0 minus 20, this will be minus 20, 6 5s are 30 minus 0, this is 30, and minus 14 minus 5 is minus 19. The next here, minus 3 into 4 is minus 12, minus 0 is minus 12, and 0 plus 18 is 18. I've got all my cofactors. And in general, whenever you take out the cofactors in this method, you better recheck once again all the determinants, because all the determinants whatever you have taken out here, because one goes wrong, you don't get one x value when we are doing in matrix method in a 5-marker problem. Okay, now that I have got my cofactors, I want you to understand these two properties. Like, it's so wonderful, you know. See, there is a certain procedure which I have followed, that too with the product of minus 1 to the power of I plus j, is it not? So we have taken out the cofactors, the corresponding cofactors with a particular procedure. Now I can take out the determinant value multiplying any row or any column by their own corresponding cofactors. See, now you know the meaning of this matrix is cofactor of 2 is minus 20, cofactor of minus 3 is 46, cofactor of 5 is 30, cofactor of 6 is 4, and so on. So I have got all the corresponding cofactors in this matrix. So it's called as matrix of cofactors. And now I shall use row number 1 here and row number 1 here also. Multiply the corresponding elements, first, second, third. I'll multiply and add, and let's see what we get. And I'll call it as delta. That's what the property tells. So delta is equal to, I shall use the first row here and the first row here, 2 into minus 20, 2 into minus 20, minus 3 into 46, plus 5 into 30. I shall use calculator. This will be minus 40 minus 3 into 46 is 138 plus 150. So 138 plus 40 is equal to 178 minus 150 is equal to, and I have got here minus 28 as my delta value. Now let us go another thing. Now I am writing here along R1. Now this I have shown you in the previous class also. Now I will go along R3. Like, irrespective of anything, any row, multiply by their own cofactors. So what I have done here is, I have taken row number 1 elements, multiplied by their own cofactors, and I have added, I have got a particular number, which I am telling it is determinant. Okay, let us go to the next. I am doing the same procedure with R3. R3 here and R3 here. So let me take, you have is equal to 1 into minus 12 plus 5 into minus 22 minus 7 into 18 is equal to, so this will be minus 12, then minus 5 2s are 10, minus 110, minus, I guess something has gone wrong, 7 into 18 is equal to 126. Yes, something is wrong here. Let me check out. So this will be minus 12. This will be 4 twos are 8 minus 30 is okay. See, I've gone wrong here. 4 twos are 8. 8 minus 30 is minus 22. Minus into minus plus 22. So this was plus 22, which means that this is going to be plus 110. Let me check. So you have 126 plus 12 is equal to 138 minus 110 is equal to 28. So once again I have got minus 28. Okay. So now in the next one along R3. Now what I am telling you is whichever row or whichever column you take. Let me take along C2, along one column also I should show you along C2. So delta is equal to, I am using column number 2 here and column number 2 here. You have minus 3 into 46, 0 into minus 19 plus 0 I shall write, plus 5 into 22. So this will be equal to, this is 3 into 46, 3 into 46 is equal to 138 plus 110. So this is equal to minus 28 once again. Now children, isn't it amazing that they have found out a procedure that in you can put any kind of numbers inside this matrix, find out the cofactors properly. You should not be making mistake the way I did now. Now after that, after following the procedure, you see that the corresponding row and its own cofactors multiplying, or any column multiplied by their own cofactors will always give you the same number, and that number is called as what? Determinant. Now this happens with any kind of numbers, I am telling you again and again, and this happens with all the square matrices only. This is a third order matrix. Like this you have a procedure to find out the determinant and their cofactors for fourth order, fifth order, sixth order, anything, but it should always be a square matrix. Okay, this is the first property what they tell. So if elements of a row or column are multiplied by their own cofactors and added, will always give you the value of the determinant. So what is that am I doing here? So delta is equal to, I shall take A11 multiplied by their own cofactors A11. Next I will take A12 multiplied by its own cofactor A12. A13 into capital A13 will always give you what? The determinant value. It will always give you a numerical value. So this may be with any row or any column. When you see the same numbers here, you will understand that one row, here I have used row 1 1 1, I have used the first row element. First row multiplied by their own cofactors will give you the determinant value. Now you know the next, I am going to the next property. I will just erase all this. We are going to the next property. I shall take the elements of one row, but I shall multiply the first row elements with some other row cofactors. So I'll use R1 and I'll use R2 here. So let us see what we get. I'll use R1 and R2. Then what happens? So 2 into 4 minus 3 into minus 19 plus 5 into minus 13 is equal to, so this is equal to 2 fours are 8, minus into minus plus, this will be 57, and this is minus 13 fives are 65. See, it's exactly equal to 0. 57 plus 8 is 65, minus 65 is 0. Now I shall use, okay, C1 and C3 I shall use. I shall use column number 1 here and column number 3. What I am doing is, I am using column number 1 elements multiplying by the cofactors of column number 3. I am using different cofactors. Okay, so now I shall take 2 into 30, then plus 6 into minus 13, plus 1 into 18. So what are we getting? 2 into 30 is 60, minus 6 3s are 18, that is 78, plus 18. See, 78 minus 78 is 0, exactly 0. Isn't it amazing? So now like this, when any row or any column elements multiplied by the cofactors of another row or column, and added, we always get what? We always get 0. This is what is your second property. Elements of a row are multiplied by cofactors of another row, then their sum is always 0. So now for example, I shall take that, I'll write it. What is that we did? A11, A11, and I shall take A21. What I am doing is, I am taking first row's elements, multiplying by the cofactors of the second row elements, A21. So A12 into A22, A13 into A23. When you add this, you exactly get 0. See, the numbers are different here. So I am taking a different row elements here. When I am taking and adding, multiplying and adding, then I get exactly 0. This is the second property. Now this shall be used in finding out the adjoint and inverse. So please remember these properties, and now let me go to the properties of determinants. These are the properties under expansion of determinant. How am I getting determinant? So how many ways can you take out the determinant? There are 6 different ways to take out the determinant along any row or along any column. And now one point to be noted here is, when I am multiplying row number 1 cofactors, I cannot take cofactors of a column. Row should be multiplied with the cofactors of another row. I cannot multiply it to the column cofactors and find out whether it is 0. It cannot happen in the second property. Of course, to take a determinant, you have to use the same row or the same column. And now this was the example for minus cofactors to be understood under expansion of determinant. Now let us go to the next part where we learn the properties under determinants. See, property number 1. Once again, this is going to be theoretical. Please understand these properties, and these properties will be well understood when we apply all these properties inside the problems. So basically, I'll rush off very quickly. Sometimes they'll ask you some proof only for 2 marks or 3 marks in the board examination. And it's very easy to prove, and please understand the property. Property number 1 tells you the value of the determinant remains unchanged if its rows and columns are interchanged. First of all, if the rows and columns are interchanged, what is it called as? It's called as a transpose. So whether you take a determinant in a way, in the same way as it is, or you interchange rows and columns, transpose it and take out the determinant, it has no change in the value. The value remains to be the same. So let us see. See, I'll say let delta be equal to determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3. I'll expand this. Is equal to A1 into B2, C3 minus B3, C2. Then this should be taken with opposite sign. I hope you have practiced. Minus A2 into, now I should take these 4 elements. That will be B1, C3 minus B3, C1 plus A3 into B1, C2 minus B2, C1. And I shall multiply that also inside. When you have theoretical proof, it's going to be lengthy like this. A1 B2 C3 minus A1 B3 C2 minus A2 B1 C3 minus to minus plus A2 B3 C1 plus A3 B1 C2 minus A3 B2 C1. Now I got my delta. Okay, I have regular way I have got my delta. Now I shall take delta dash. What do you mean by delta dash? I am going to apply whatever they have told in the property. Now this delta is going to be standard. I will keep it as it is till the end of all the properties. Every property you need this expansion, the general expansion delta. And now don't take the elements as A11, A12, A13. That will become tedious to expand. So don't take it in a very simple way with a single digited subscriptions. Okay, now delta dash. What is the property telling? The property tells that if you interchange rows and columns, the determinant value will not change. I will interchange and see now. So I shall interchange row 1 and row 3, for example. R1 interchange. So sorry, what am I doing? I should be interchanging all the rows and columns, is it not? So all rows and columns I'll interchange. Row number 1 will be A1, row number 1 will become column number 1 here. A1, A2, A3 like this. B1, B2, B3, C1, C2, C3. And again I'll expand and see whether I'm going to get the same kind of elements with the same signs also. So let me see. A1 into B2, C3 minus B3, C2 minus B1 into A2 C3 minus A3 C2 plus C1 into A2 B3 minus A3 B2. And whenever you give some proof like this, always make it a point that you write it in ABC every time, orderly. Now I am going to multiply each one of them. A1 B2 C3 minus A1 B3 C2 minus A2 B1 C3 minus C2 minus plus A3 B1 C2 plus A2 B3 C1 minus A3 B2 C1. Okay. Now let me check. A1 B2 C2, oh, something is wrong here. C3, this is A1 B2 C3, A1 B2 C3. Next you have A1 B3 C2, A1 B3 C2 with minus, we have got the same. Then you have A2 B1 C3, A2 B1 C3 with minus, same thing. A3 B1 C2 is here with plus, I have got plus. 2 3 1 is here with plus, and the last one remains the same. So we have got the same thing. So in spite of interchanging rows and columns or transposing the determinant will not change its value. Because now how it is useful, I'll tell you. Now for example, say example, I shall take one delta is equal to 1, 2, 3, 4. This will be equal to 4 minus 6, which is equal to minus 2. Delta dash is equal to 1, 2, I'll write like this. 3, 4, I shall write like this. Now what is it? 4 again minus 6 is equal to minus 2. This is an example. Delta and delta. How it will be useful in the problems when you are doing regarding this determinants is, you will get one problem 1a squared, 1b b squared, 1c c squared. You need to do this problem. See, 1 1 1 is column wise, and many a time students will be comfortable if this 1 1 is row wise. So this determinant can be transposed and done 1 1 1 A B C, then A squared B squared C squared. We have interchanged rows and columns. So whether you do the problem in this way or you transpose it and then do, you get the same answer. So it is useful in that way. Few of them will be comfortable with column ones, and few of them will be comfortable with row ones to do the transformations. So whichever you want, you can do. Suppose you are not comfortable, you can transpose and continue. And now let's go to property number 2. Property number 2. Okay, now here instead of interchanging all rows and columns, if you interchange only 2 rows or only 2 columns, then what happens? Then the sign of the determinant will change. I shall tell you the example and then get into the the regular delta. I forgot and erase this delta also. Okay, let me go for an example for this property. I shall take delta is equal to 2 3 5 minus 6, something like this, and I shall take expanded. This will be minus 12 minus 15 is equal to minus 27. Okay, so now I'll interchange row 1 and row 2. R1 interchange R2, I shall say. So delta dash is equal to 5 minus 6 goes to the top, 2 3 comes down, and I'll expand. 5 3s are 15 plus 6 2s are 12, which is equal to 27. See, here it is minus 27 and here it is plus 27. So you got delta dash is equal to, I am not transposing it, I am telling it as delta dash, means the new delta. Whatever the change they are asking us to do, we do the change, and that new delta is called as delta dash. So delta dash is not the same as delta, but it is opposite in sign. Here is minus 27 and here it is plus 27. This is the meaning of the property, where if you interchange any 2 rows or if you interchange any 2 columns, then the sign of the determinant value changes. Plus becomes minus or minus becomes plus. And now here again you cannot interchange one row and one column, it's impossible. So any 2 rows or any 2 columns. So let us go to our standard delta. This I shall keep as it is. I shall repeat. You have A1 B1 C1, A2 B2 C2, A3 B3 C3 is equal to A1 into B2 C3 minus B3 C2 minus B1 into I think I have, okay, let me take like this, minus B1 into A2 C3 minus A3 C2 plus C1 into A2 B3 minus A3 B2, and I shall multiply this inside is equal to A1 B2 C3 minus A1 B3 C2 minus A2 B1 C3 minus into minus plus A3 B1 C2 plus A2 B3 C1 minus A3 B2 C1. Okay, I have expanded. I'll keep this standard as it is. And now property, according to property number 2, I need to change any 2 rows or 2 columns. Whenever you want to do some proofs, go for the simplest one. Now what I'll do is R1 and R2 I'll interchange. I shall interchange R1 and R2. So your delta dash, the new delta becomes, here you will have A2, B2, C2 and row number 1 will come to the second place A1, B1, C1, A3, B3, C3 I'll keep as it is. We shall expand, then you have A2 into B1 C3 minus B3 C1 minus B2 into A1 C3 minus A3 C1 plus C2 into A1 B3 minus A3 B1. Okay, we'll expand and check now. This will be equal to A2 B1 C3 minus A2 B3 C1 minus A1 B2 C3 plus A3 B2 C1 plus A1 B3 C2 minus A3 B1 C2. Okay, I'll check the previous one and this one. See A1 B2 C3 1 2 3. Where is 1 2 3? Let me check. 1 2 3 is with minus here, but here it is with plus. Okay, I'll go to the next one. 1 3 2. Where is 1 3 2? You have 1 3 2 here. See 1 3 2 is having minus here. A1 B3 C2 is having minus, but here you have plus. So every other element, every other term in this and this are having the opposite sign. So what I'll do here, to prove that delta dash is equal to minus of delta, I shall take out minus common and you will get A2 B3 C1. This minus I made as plus. This becomes minus A2 B1 C3 plus A1 B2 C3. This plus becomes minus A3 B2 C1. This becomes minus A1 B3 C2 plus A3 B1 C2. And now this is nothing but our previous delta. You can check 2 3 1 with plus, 2 3 1 with plus. Next 2 1 3 with minus. So 2 1 3 with minus, and then 3 2 1 with minus, 3 2 1 with minus. Like this you have got the entire delta here inside the brackets. So it is minus delta. So we have proved the property. If you interchange any 2 rows or any 2 columns, a minus comes out. The value of the determinant changes by its sign. And now let us go to, I'll keep this delta standard as it is and we'll go to next property. Property number 3. If any 2 rows of a determinant are identical elements, then value of the determinant is 0. Okay, for this you don't even need a delta. See, I shall take delta dash directly. I shall say R1 is equal to R2. They are telling that if 2 rows are identical, then the determinant value will be 0. It will vanish. So let us see. So directly in my delta, in the delta dash, I will write R1 and R2 ditto. So R1 will be A1 B1 C1. R2 also will be A1 B1 C1. R3 I'll write A3 B3 C3. Okay, let us expand. A1 into B1 C3 minus B3 C1 minus B1 into A1 C3 minus A3 C1 plus C1 into A1 B3 minus A3 B1. I shall multiply inside. This is equal to A1 B1 C3 minus A1 B3 C1 minus A1 B1 C3 plus A3 B1 C1 plus A1 B3 C1 minus A3 B1 C1. Let us check out. You have A, B, C, right? 1, 1, 3. Another 1, 1, 3 is here. This is having plus or this is having minus. These two will get cancelled. 1, 3, 1. You have 1, 3, 1 here. This is with plus and this is with minus. So these two gets cancelled. And obviously the other two will get cancelled. Therefore this answer delta dash is equal to 0. So when is delta dash equal to 0? If two rows or any two columns are identical, if the same elements are present in two rows or two columns, the determinant value is 0. This was property number 3. And now once again I am going to retain delta as it is. We will go to the next property. What does it tell? If each element of a row of a determinant is multiplied by a constant k, then its value gets multiplied by k. Now what is the meaning of this? I shall give you an example for this, then you will clearly understand. Delta is equal to, so I shall take 2, 1, minus 3, 5. The answer will be 5 2s are 10 plus 3, which is equal to 13. Now what I will do, delta dash, I shall multiply, see if each element of any one row or any one column should be multiplied by one constant k. So I shall multiply R1, I shall multiply by 2R1. I will multiply by 2. So delta dash will be determinant of 2 2s are 4, 2 1s are 2, minus 3 5 is equal to 5 4s are 20 minus 6, minus into minus plus, so this is equal to 26. So see that this has been multiplied by 2 into 13. So you got 2 times delta. Delta dash is equal to 2 times delta. And this was the reason in the last class I told you that in determinant, if you have to take out anything common, you have to take out from one row or from one column. You cannot take out the common from all the elements together as one element. No. You can take out 3 numbers common, from one from R1, one from R2 and one from R3. Every row you can take out common, even minus, or if you want to take out anything, any number common, columns also, it is single column wise you can take out the common. So here you see, if one row has been multiplied by a scalar 2, the entire determinant only is multiplied by 2. Delta dash is equal to 2 times delta. Okay, so this was your property number 4, and to prove this we will multiply, we will do like this. So delta dash, so let me multiply R1, let it become k times R1. To prove this I shall multiply by k. And one more thing, whenever they ask you to prove, you cannot prove with an example the way I gave you now. There is no numerical example accepted for the proof of any property like this. You have to use a generalized element A1, B1, C1, A2, B2, C2 in this way. Okay. So now delta dash is equal to, I shall multiply this row by k, it becomes KA1, KB1, KC1, A2, B2, C2, A3, B3, C3. Now I shall say KA1 into A2, I am sorry, B2, C3 minus B3, C2 minus KB1 into A2, C3 minus A3, C2 plus KC1 into A2, B3 minus A3, B2. This is equal to, now you see every element is having, every term is having k common, k, here k and here k. So I shall remove k common and then multiply this a1 inside, that will be a1 b2 c3 minus a1 b3 c2 minus a2 b1 c3 plus a3 b1 c2 plus a2 b3 c1 minus A3 B2 C1. Okay, and now what you see, after multiplying you see that this delta is back here. So this becomes delta. So I have got delta dash is equal to k times delta. So if you multiply any one row with the scalar k, then the entire delta itself is multiplied by k. This is what the property tells. So with that we have completed property number 4 proof, and now let's go to the next property. And these from property 4, it's extremely important for exam if by chance they ask for proof, and I guess by this time you would have understood how to do it in a generalized way. Now you see property number 5, if some or all elements of a row, of a column, of a determinant are expressed as sum of two terms, then the determinant can be expressed as sum of two determinants. What is the meaning of this? I shall tell you with an example. say example, suppose delta you have 2 plus 5, 3 minus 2, and then you will have 1, 3. If you have like this, if one row elements are addition of two terms, then you can write this as addition of two determinants. So this will be equal to, I shall take first element 2, first element 3, and then 1, 3. Next plus I will say, next I will take the second elements 5 minus 2, 1, 3. These two will give you the same answers. Or if it is addition of three elements, so delta is equal to, I shall say 2 plus 5 minus 7, 3 minus 2 plus 4, 1, 3. If it is like this, if elements of any one row is addition of three terms, then this total determinant can be written as sum of three different determinants using the first element, second elements and the third element. See, this will be equal to, I shall take 2, 3 first elements, 1, 3 plus, next I will take the second elements, 5 minus 2, 1, 3. Next I will take the next elements, minus 7, 4, 1, 3. You get the determinant like this. So this is the meaning of that property. And in this property, if one row is addition of two elements, if another row also is addition of two elements, you have to do one step after another step. Now for example, delta is equal to, you have 2 plus 5, 3 minus 2. If this was 1 plus 7 and 3 minus 5, if you have like this, now this is equal to, I shall take first elements 2, 3. This 1 plus 7, 3 minus 5 I should write as it is. Next I shall take second elements 5 minus 2, 1 plus 7, 3 minus 5 as it is. Next I shall take the top elements as it is, 2 plus 5 and 3 minus 2. Here I shall take the first elements 1, 3 plus. Next I shall take the second element 7, 5, 7 minus 5 in the second row. First row I should keep as it is, 2 plus 5, 3 minus 2. Now this is the meaning of the property. If there is one column or one row elements which are addition of two or three elements, then we can separate the determinants as the sum of that many determinants. How many terms are there? That many determinants we can write it as. Now this is the meaning of the property. Now let us go to the proof of this. And when you are doing the proof of these determinants, now that we have already proved for the previous determinants, we can use those results inside this. So let us start the proof of this. I shall say delta dash. Now what is the change I should do? I shall I shall add A1, B1, C1 with LMN. Let us see what we get. See, I shall write delta dash A1 plus L, B1 plus M, C1 plus N, and this will be A2, B2, C2 second row, A3, B3, C3 third row. Okay. Now how do I push it? I will expand as usual. So that will be A1 plus L into B2 C3 minus B3 C2. Next, minus of B1 plus M into A2 C3 minus A3 C2 plus C1 plus N into A2 B3 minus A3 B2. You know what I can do now is, I will take A1 into B2 C3 minus B3 C2. Next I shall take minus B1 into A2 C3 minus A3 C2. So I am taking A1, I am taking B2, I am taking B1, now I am taking C1 plus C1 into multiplication of this A2 B3 minus A3 B2. Don't you see that all these are also multiplied by the second terms? So now I shall take all the second terms. So I shall say plus L into so much, plus L into the same thing, then minus M into the same thing, and then plus N into the same thing. So I'll repeat here, B2 C3 minus B3 C2. This will be A2 C3 minus A3 C2. and this is A2 B3 minus A3 B2. Now what happens? If the multiplication, if this is multiplied inside, I know I am going to get the delta value, is it not? But this writing only so much, the first row whatever, plus indeed I have continued, this much is the expansion of this actually. So now I can break this up into two determinants, is it not? See, I am getting A1 B2 C3 minus B3 C2 and something whatever you have got here. Writing that in the determinant form, I will get this equal to determinant of, the first one is, these are the first row element. So I have got A1 B1 C1, A1 B1 C1. Now this is B2, you have B1, sorry, this is A2 B2 C2 and then A3 B3 C3. Let me check. A1 into B2 C3 minus B3 C2 you have got here. Then minus B1 into A2 C3 minus A3 C2 which you have got here. So I have written the first row in the determinant form. So now you have the same thing here except that your A1, B1, C1 are replaced by L, M, N. So I shall replace L, M, N and you have got again A2, B2, C2, A3, B3, C3 here. So see, the determinant where one row elements was addition of two terms has become the summation of two determinants where the first determinant is taking the first values and the second determinant is taking the second values. And this goes on whenever there is addition or subtraction. If there is minus common, if there is minus common, you can take this minus and write there, or you can write plus here and write all with minus. So sum of any two elements, I mean any row is having sum of two or three determinants, that particular sum of that many determinants can be written. Now I shall go to the next property, again retaining the first determinant expansion as it is. This is A1 B1 C3, this is A3, this A3 B1 C2 plus this is A2 B3 C1 minus, okay, minus this is B2 C1, okay. And now let me go to the next property. Property 6 tells you like this: if to each element, okay, if to each element of any row or column of a determinant, the equi-multiples of corresponding elements of another row are added, value of the determinant does not change. This is so amazing. I will give you numerical example. See, I will say 1, 2, 3, 4 and I will take the expand the determinant is 4 minus 6 which is equal to minus 2. Now what I will do, I will multiply row number 1, I will add row number 1 with multiples of 2 of second row. You know, I will write like this: R1 I am changing, I am transforming R1. How am I changing? I am changing like this: R1 plus 2 times R2. I will multiply 2 to R2 and then add it to R1. Okay, so delta dash will be equal to, this is my delta. What am I doing? Row number 1, I will multiply this by 2 and add it to here. 3 2s are 6, 6 plus 1, 7. 4 2s are 8, 8 plus 2, 10. 3, 4. I will expand the determinant. I have done R1, I have added with 2 times R2. So let me see, 7 4s are 28, minus 3 10s are 30. See, still it remains to be the same. I will do another transformation here only. I will take column number 1 to be 3 times column number 2. So, okay, minus 3 times column number 2, I will take with minus sign also. So, I will say delta dash is equal to, column number 1 I am changing, I am multiplying column number 2 by minus 3. 2 into minus 3 is minus 6, 1 minus 6 is minus 5. Next, I will multiply this by minus 3, 4 into minus 3 is minus 12, 3 minus 12 will be minus 9 and 2 4 I will retain as it is. Let me expand. So now I have got minus 20 plus 18, 9 2s are 18. So this is equal to minus 2. So irrespective of whatever the scalar you take, whatever the constant you take, multiply to some row, add it to another row or add it to another column, the determinant value will not change. It will remain to be the same. That is the meaning of this this property. So now how do you prove this? So I shall go multiply, and now in this proof we are going to use the previous proofs also results. So I'll say I will multiply R1 as R1 plus K times R2. So delta dash will be equal to A1 plus K times A2, B1 plus K times B2. I am multiplying K to row number 2 and adding it to row number 1. C1 plus K times C2, and this will be retained as it is R2 and R3, A2, B2, C2, A3, B3, C3. Now let us try to expand this. This is equal to A1, what is this? A1 plus K times A2 into B2 C3 minus B3 C2 minus of B1 plus K B2 into A2 C3 minus A3 C2 plus C1 plus K C2 into A2 B3 minus A3 B2 is equal to, now I shall take A1 and then I shall take B1, then I shall take C1 and write, we had used this before also. So I shall write A1 into B2 C3 minus B3 C2 minus B1 into A2 C3 minus A3 C2 plus C1 into A2 B3 minus A3 B2. Now I shall continue with this KA2 minus KB2 and then KC2. So is equal to K into the same thing, KA2 into the same thing minus KB2 into the same thing, then plus KC2 into the same thing. So we'll retain now whatever you have here inside. This will be B2C3 minus B3C2. This will be A2C3 minus A3C2. This will be A2B3 minus A3B2. Now I can write this in the determinant, is it not? As we did in the previous two previous property, we'll break this in. We'll write the same thing, and something went wrong here when I should not write equal to A1, this one, plus it is continuing. Is it not? So now I have expanded the same determinant in 2 lines here. This much to this much is one step. I shall write the first row here as the determinant form, where you have the first row elements as A1, B1, C1. This is your regular determinant, A1, B1, C1, and inner terms will give you the second row as A2, B2, C2 and A3, B3, C3. And now if you compare, you can see that this is the determinant of the delta itself. And this next, again these also I shall write as the same, where the inner terms are same. So second row A2, B2, C2, third row A3, B3, C3 are same, whereas the first row will be different, KA2, KB2, KC2. So you have KA2, KB2, KC2. Now I split it. Now the sum of, because one determinant was, you know what, actually I'll tell you, you can use the previous determinant because you have A1 plus K2, you need not go for this expansion. Here itself you can split this into 2 terms. So directly from here you can write like this, but I only showed you that you can write this also. If it is for 3 marks or 4 marks. See, if it is for 2 marks, you can directly split this into these 2 determinants using the previous determinant property. Using the previous property, I can always directly do it. And now after doing it, this is equal to, so this was my delta dash. Delta dash is equal to, this is nothing but delta, that is this delta. Then plus, here the first row is having K common, I shall take out K common, then you have A2, B2, C2, A2, B2, C2, A3, B3, C3. What do you find? Use the previous property. You have 2 rows identical. So this will be delta plus K into 0. Why is it 0? Because R1 is similar to R2. Whenever R1 and R2 have the same elements, any two rows or any two columns having the same elements, determinant value is going to be 0. So this determinant value is 0. So delta plus 0, delta dash. So this implies delta dash is equal to delta in spite of adding k multiples of another row to the first row or the second row or the third row. Any one row multiples can be added to another row, still the determinant does not change. The value of the determinant does not alter at all. And now after this we are going to the next property, property number property number 7. Now this is very simple. If all the elements of any one row are equal to 0, then the determinants will be 0. So this, there is no proof, children, but I can write directly anyway. So see, if you have 0, 0, 0, 1, 2, 3, 4, 5, 6, this will be 0 into something plus 0 into something plus 0 into something, which will be totally equal to 0. So as such, there is no proof required. I just wanted you to, this is an extra statement which is not in your textbook. If any one column or any one row is, all the elements are equal to 0, then the determinant value is always 0. And the next one, the value of a triangular determinant is the product of the principal diagonal elements. What is the meaning of this? This is, again I'll go for a numerical example first. Delta is equal to, if you have 1, 2, 3, here the lower triangle will be 0 and you have minus 1, 2 and this will be 2, suppose. What is the value of this determinant? It will be the product of the PD elements. This is called as the triangular determinant because the lower triangle elements are all equal to 0. Irrespective of the upper triangle elements being anything, the determinant value will be the product of the PD elements. So delta will be equal to 1 into minus 1 into 2, which is equal to minus 2. Let us expand. So delta is equal to 1 into minus 2 minus 0, minus 2 into 0 minus 0, plus 3 into 0 minus 0. When you expand, you will be getting 1 into minus 2 only, these are zeros. So whenever you have triangular determinant, so now I shall go tell it in terms of A1, B1, C1. See, delta is equal to, suppose you have A1, this will be 0, 0, 0, this will be A2, B2, and the third row will be A3, B3, C3. Upper triangular elements are all equal to 0. So the determinant value will be equal to the product of the PD elements. A1, B2, C3 will be the answer. This is also the answer if the lower triangle is 0. A1, B1, C1. This will be 0, 0, 0. This will be B2, C2, and this will be A3, B3, C3. Okay, the lower triangle is 0. So still the answer will be product of the PD elements A1, B2, C3. Now a point to be noted is the other diagonal is not considered in all these properties. The only diagonal which we consider is from left top to right bottom, the principal diagonal only. There is only one principal diagonal from left top to right bottom. The other diagonal is not considered. So whenever we say triangular determinant, it's only this triangle and this triangle that we consider for the determinant. And now in this, of course, if you have these as 0, 0, 0, both upper triangle and lower triangle both being zeros also, the determinant value will be equal to the product of the PD elements. Okay, these were all the properties, and after this, in the next session, we are going to learn the problems based on all these properties, and they are very, very interesting. And these, whatever the exercise now we are going to do, that will be very important for your board examination as well as your JEE examination. You should learn to tackle the transformations which comes in the determinant problems. So when you look at the problem, how to identify. Now I shall be telling you type number 1, type number 2, type number 3 problems in determinants. So you have to be careful where we'll always be using these properties, and all these properties in one problem we can use several properties or maybe only one property also. Using that we will be reducing the determinant to a certain answer. Thank you.